Welcome to a new lesson in the VTskills course. Today we'll dive into proximal sensors, essential tools for gathering data directly from the vineyard to support smart, sustainable decisions. Here's an overview of the topics for this lesson. Section 1, General Introduction. What is proximal sensing? Proximal sensing is the use of technologies that allow data to be collected in close proximity to the target of analysis, be it the soil, the plant, or the immediate environment. Unlike remote sensing, such as satellites or drones, these sensors are located directly in the field, often mounted on tractors, fixed stations, mobile platforms, or even handheld. These sensors measure variables such as temperature, soil moisture, vegetation reflectance, electrical conductivity, or chlorophyll fluorescence, among many others. Because they are so close together, they provide data with high spatial accuracy and temporal frequency, ideal for monitoring the crop line by line or even plant by plant. This makes proximal sensing an essential tool for precision viticulture, as it allows detecting differences within the same plot and adapting management decisions such as irrigation, fertilization, or harvesting in real time. Moreover, as it is not affected by weather conditions such as cloud cover or rain, it is very reliable for continuous monitoring. What is proximal sensing for in viticulture? Proximal sensing is key to more efficient, accurate, and sustainable vineyard management. It has multiple applications. 1. Irrigation management. Using thermal sensors, which measure leaf temperature, or soil moisture sensors, it is possible to identify areas where the vine is under water stress. This allows irrigation to be applied only where it is necessary, improving water use efficiency. 2. Nutritional diagnostics. Sensors such as reflectance sensors or chlorophyll meters help to estimate the amount of nitrogen available to the plant. Fertilization can then be adjusted precisely to avoid excesses or deficiencies. 3. Early detection of diseases. Certain sensors can detect physiological or structural signals in the plant before symptoms are visible to the human eye, facilitating early and targeted treatments. 4. Monitoring of ripening. Fluorescence, reflectance, or spectroscopy sensors make it possible to assess fruit development, such as anthocyanin, sugar, or chlorophyll content. This helps to decide more precisely when to harvest. 5. Selective harvesting. Using vigor, ripeness, or quality maps, it is possible to segment the vineyard and harvest by zones, which improves the uniformity of the batches of grapes and enables differentiated wines to be made. What is the role of IoT in viticulture, and how does it relate to proximal sensors? The IoT, or Internet of Things, is a network of physical objects, sensors, weather stations, irrigation valves, etc., connected to the Internet. Its value in viticulture lies in transforming sensing into useful action. Thanks to IoT, sensors that are in the field collecting data, for example, soil moisture or leaf temperature, can send that information in real time to cloud platforms. From there, the data is automatically analyzed and can be used for further analysis. Generate alerts, for example, if there is a risk of frost or if an area becomes water-stressed. Activate automated responses, such as turning on an irrigation system. Viewed from a mobile app, allowing the farmer to monitor and make decisions from anywhere. In addition, IoT is the foundation on which decision support systems, DSS, operate, helping to process large volumes of data and provide concrete recommendations based on validated models. What are the advantages of proximal sensing over traditional techniques in the vineyard? Traditionally, vineyard management has been based on experience, visual observation, and manual sampling. While these methods still have value, they have limitations. They are not objective, they cover few plants or areas, and they do not allow a rapid response based on quantifiable data. Proximal sensing offers a profound transformation. 1. Accuracy and objectivity. The sensors measure real and continuous parameters such as humidity, temperature, or chlorophyll. This reduces uncertainty in decision-making. 2. Early detection of problems. Many sensors can identify physiological signals, such as water stress, nutrient deficiency, or onset of disease, before they are visible, allowing preventive action to be taken. 3. Zone-specific decisions. Thanks to mapping and high resolution, differentiated treatments can be applied according to the needs of each part of the vineyard. 4. Input savings. By acting only where it is needed, the use of water, fertilizers, or plant protection products is reduced, which reduces costs and improves sustainability. 5. Historical database. Systematic data collection allows for trend analysis, evaluation of past practices, and design of continuous improvement strategies. In short, sensing transforms vineyard management from a reactive and general to a proactive and targeted approach, which is key in modern viticulture. Section 2, Types of Sensors. Soil is a critical component for vine development. Its analysis by means of sensors allows us to know its structure, fertility, humidity, and other relevant parameters without the need for invasive or costly sampling. 1. Reflectance sensors work by projecting light onto the soil, usually in the visible and infrared range, and measuring what is reflected. They are used to estimate properties such as texture, surface moisture, or organic matter content. 2. Electrical conductivity. 1. EMI, electromagnetic induction, measures the apparent conductivity of the ground without physical contact. Ideal for quick mapping and covering large areas. 2. Electrical resistivity, uses electrodes that inject current into the ground and measure resistance. It allows a deeper and more detailed analysis, although it requires more laborious installation. 3. Moisture and temperature sensors. These are inserted into the soil to continuously record the evolution of water content and temperature, helping to decide when and how much to irrigate. 4. Electrochemical sensors measure the concentration of nutrients in solution, such as nitrates or potassium, or pH. They can be installed in a fixed installation or in portable devices for rapid diagnosis. 5. Other advanced technologies. 1. Ground penetrating radar, GPR, emits electromagnetic waves that reflect in subsurface layers, useful for studying stratification of roots. 2. Gamma radiometry, captures natural radiation emitted by certain elements in the ground, useful in geological mapping. 3. Mechanical or resistant sensors, useful for analyzing compaction, especially in soils subjected to machinery. The combination of these sensors allows the generation of soil variability maps, the identification of problem areas, and more accurate and efficient agronomic management. Here you can see some examples of soil sensors commonly used in vineyards. Soil moisture probes, FDR and TDR in precision viticulture. Moisture probes are fundamental tools for rational irrigation management in the vineyard. The most commonly used technologies are FDR, frequency domain reflectometry, and TDR, time domain reflectometry. They both measure the volumetric water content in the soil, but do so using different electrical principles. How do they work technically? TDR, time domain reflectometry, sends an electrical pulse along a metal probe inserted into the ground. It measures the time it takes for the signal to reflect. The higher the water content, the slower the return, as water has a much higher dielectric constant than air or solids. FDR, frequency domain reflectometry, generates a high-frequency electric field and measures the capacitance of the soil to store this energy. This capacitance also correlates with moisture content. Both systems require calibration with the local soil type to ensure accuracy. Multi-depth probes, 30, 60, 90 centimeters, can be installed to observe the root profile. Applications in viticulture. Real-time water stress monitoring. Demand irrigation. Decide when and how much to irrigate according to defined thresholds. Monitoring of the water profile in different soil layers. Phenological prediction models integrated with DSS. Advantages. Accurate and continuous reading. Installable in a network with wireless transmission or local storage. Low interference from salinity or temperature, especially in TDR. Compatible with climate, evapotranspiration, and DSS models. Case study, Demeter Project, EU. In vineyards in southern France, TDR probes were installed at 3 depths in irrigated and non-irrigated plots. The information allowed a 20% reduction in water applied without affecting yield and quality. Irrigation alerts were integrated into the DSS field app. EMI, electromagnetic induction technology for characterization of grapevine soils. Electromagnetic induction, EMI, is a non-invasive technique for measuring the apparent electrical conductivity, ECA, of soil at different depths without the need for physical contact. It is particularly useful in precision viticulture to characterize soil variability quickly and reliably. How does it work technically? The EMI sensor consists of an emitting coil that generates a primary electromagnetic field. This field induces eddy currents in the ground, which in turn generate a secondary electromagnetic field. A receiver coil measures this response, which depends on the soil's ability to conduct electricity. The response varies according to soil moisture, texture, clay-sand ratio, salinity, temperature, and organic matter content. The reading depth depends on the design of the equipment, vertical or horizontal configuration of the coils, and can be up to 1.5 meters. Applications in viticulture. Zoning of the vineyard allows the division of plots into homogeneous units on the basis of their physical properties. Variable irrigation scheduling by identifying more retentive or more draining areas. Design of sampling networks or fixed sensor locations. Rootstock or variety selection according to soil type. Advantages. No direct contact with the ground is required. High reading speed. A farm can be mapped in a few hours. It can be mounted on a vehicle and geo-referenced. Compatible with other information layers, NDVI, climate, yield. Case study. VTskills Project, Spain. Use of EMI sensor in vineyards in La Rioja to characterize soil heterogeneity. Based on the maps generated, 3 differential management zones were defined. Drip irrigation was adjusted and a 15% improvement in water efficiency and a reduction in ripening variability was verified. Electrochemical soil sensors, pH, nitrate, and nutrients available in real time. Vine nutrition is key to vegetative productive balance, stress resistance, and fruit quality. Traditionally, soil chemical analysis requires sampling, drying, analysis laboratory, and time, but electrochemical sensors allow immediate results to be obtained in the field. How do they work technically? These sensors consist of pairs of electrodes. One is the reference electrode, which provides a constant potential. The other is sensitive to the specific ion, and its potential changes depending on the activity of that ion in the soil solution. The potential difference between the 2 electrodes is proportional to the ion concentration according to the Nernst equation. It is used to measure pH, essential for nutrient availability. NO3 nitrate, direct indicator of available nitrogen. K+, potassium, essential for ripening and water metabolism. Sensors for NH4+, K2+, or PO43 are also available, although less common. Applications in viticulture. Rapid diagnosis of nutritional deficiencies or excesses. Fertigation adjustment in fertigation or foliar applications. Continuous monitoring in leaching-sensitive soils. Use in nutrition models integrated into DSS or farming apps. Advantages. Immediate results in the field. It avoids costs and laboratory time. Portable or integrable equipment in multi-parametric probes. Useful for organic or biodynamic viticulture, where intervention is minimal but strategic. Case study. INEA trial, Chile, https://www.inea.cl/in Cabernet Sauvignon vineyards, a multi-parametric sensor system was used to measure pH and NO3 in different soil managements, cover crops, tillage, compost. Significant differences in nitrogen availability were detected in real time, which allowed adjusting compost doses and avoiding unnecessary applications of mineral fertilizers. What sensors are used to monitor the state of vegetation in viticulture? Vegetation sensors make it possible to assess the physiological and structural state of the vine without the need for destructive intervention. They can be classified into several groups according to the physical principle they employ. 1-dot reflectance sensors. 1-dot, they capture light reflected by leaves in specific bands, visible infrared red edge. 2-dot, they allow the calculation of indices such as NDVI, GNDVI, OSAVI, used to estimate vigor, stress, or maturity. 3-dot, they include RGB basic, multispectral, 4 and 6 bands, and hyperspectral, tens or hundreds of bands sensors. 2-dot thermal sensors. 1-dot, they measure the temperature of the canopy or leaves. 2. A thermally stressed plant closes its stomata, transpires less, and heats up more. 3-dot. They are very useful for water stress monitoring and irrigation management. 3-dot fluorescent sensors. 1-dot, they detect the emission of light by chlorophyll after absorbing radiation. 2-dot, They are often used to assess photosynthetic activity and detect stress before it becomes visible. 3-dot tools such as Dualex or Multiplex are designed for vineyards. 4-dot transmittance sensors, SPAD or at-leaf type. 1-dot, they measure how much light passes through the leaf, especially in the red and infrared range. 2-dot it correlates with the amount of chlorophyll, which in turn is related to the nitrogen content. 3-dot, they are inexpensive, portable, and easy to use in the field. 5-dot 3D structural sensors. 1-dot LiDAR generates a 3D point cloud to measure canopy height, density, and volume, key for targeted treatments or selective mechanized harvesting. 2-dot ultrasonic use sound waves to measure the distance to the canopy and estimate its volume. Each sensor has advantages depending on the application, and many can be combined on mobile platforms, tractors, drones, robots, to obtain a complete picture of the state of the vineyard. Here you can see some examples of different types of vegetation sensors commonly used in vineyards. Here are a few more examples. SPAD sensor, direct and fast measurement of leaf chlorophyll in viticulture. SPAD, Soil Plant Analysis Development, is a portable sensor widely used in vineyards to estimate the chlorophyll content of leaves, which allows indirect inference of the nitrogen nutritional status of the vine. How does it work technically? This sensor performs an optical measurement by transmittance. It emits light in two wavelengths, red 650 nanometers and near infrared 940 nanometers. Leaf tissue absorbs more red light when it contains more chlorophyll. SPAD measures the amount of light that passes through the leaf. The result is converted into a relative index, SPAD value, correlated with the chlorophyll content. It does not measure nitrogen directly, but there is a strong correlation between SPAD and N in leaf. SPAD values can be calibrated with laboratory analysis to estimate variety, phenology, or zone-specific thresholds. Applications in viticulture. Assess nutritional status in real time. Adjust nitrogen fertilizer dosage, foliar or fertigation. Avoid excess N, which can increase excessive vigor and reduce grape quality. Compare performance between plots, rootstocks, or treatments. Advantages. Portable, inexpensive, and non-destructive. Ideal for weekly monitoring during key phases such as pre-flowering or veraison. Minimal training required. Some models allow data logging via Bluetooth or mobile app. Case study. Tempranillo Vineyard in Castilla-La Mancha. A weekly measurement campaign with SPAD was carried out for 3 months. Significant differences were detected between rootstock and compost treatments. The information allowed a 30% reduction in the nitrate dose in one of the areas, with no impact on yield or quality. Multispectral sensors and vegetative index analysis, NDVI and NDRE in viticulture. Multispectral sensors allow estimating the physiological state of the vine without contact, quickly and on a large scale. They are one of the most popular tools in precision viticulture, whether mounted on drones, tractors, fixed towers, or even handheld devices. How do they work technically? These sensors record the amount of light reflected by the leaves, mainly in different spectral bands. Red, absorbed by chlorophyll. Near infrared, NIR, reflected from healthy, dense tissues. Red edge, transition between red and NIR, very sensitive to chlorophyll content. With these bands, vegetative indices are calculated, such as NDVI, Normalized Difference Vegetation Index. NDVI =sign NIR red/NIR plus red reflects vegetative vigor and leaf cover density. NDRE, Normalized Difference Red Edge Index. NDRE =sign NIR red edge/NIR plus red edge. More accurate than NDVI for assessing chlorophyll content, especially at advanced stages of cultivation or in high-density vineyards. Applications in viticulture. Vigor and ripeness maps for selective harvesting. Nutritional diagnosis, detect deficiencies before visual symptoms appear. Variable pruning and topping, depending on vegetative development. Monitoring of phenological development and intraplot variability. Advantages. Rapid, massive, and non-destructive reading. It generates georeferenced maps. Easily integrated with decision support systems. Compatible with other layers, soil, irrigation, climate, yield. Case study. winery in Ribera del Duero, Spain. With tractor-mounted multispectral sensors, NDVI maps were generated throughout the cycle. 3 vigor zones were defined. At harvest, they were harvested separately and vinified separately. The medium vigor lot had the best quality yield ratio, which allowed agronomic practices to be adjusted in subsequent seasons. Thermal sensor in viticulture, early diagnosis of water stress. Thermal sensors measure the surface temperature of vine leaves, which is directly related to the water status of the plant. They are widely used because of their ability to detect stress before it is visible to the naked eye. How does it work technically? Plants regulate their temperature by transpiration. When the soil has sufficient water, the stomata open and the water evaporates, cooling the leaf. If there is a water deficit, the stomata close to prevent water loss, and the leaf temperature rises. The thermal sensor measures the infrared radiation emitted by the leaf and using conversion algorithms estimates its actual temperature. This reading is compared with wet and dry reference leaves to calculate the actual temperature. CWSI = T leaf T, wet T, dry T, wet. This index ranges from 0, no stress, to 1, maximum stress, and can be used to decide when to apply irrigation or to evaluate the effectiveness of water management strategies. Applications in viticulture. Real-time monitoring of water stress. Adjustment of irrigation on demand or by zones. Selection of the most water-efficient rootstocks. Integration with DSS for predictive irrigation modeling. Advantages. Rapid and non-destructive measurement. High sensitivity to water change. It can be mounted on drones, vehicles, or fixed stations. Useful in controlled deficit irrigation systems. Case study. Vineyards in southern Italy, Nero d'Avola. Thermal cameras installed on tractors were used to assess water stress on a weekly basis. Irrigation times were adjusted by blocks, resulting in a 25% reduction in water consumption and an improvement in the ripening balance of the grapes. Comparison of proximal sensor technologies in viticulture. In precision viticulture, there are various types of sensors that can monitor both the state of the soil and the plant. Each technology is based on different physical principles, and the choice depends on the variable to be measured, the desired level of precision, the available budget, and the type of vineyard management. Reflectance sensors are the most common sensors. They work by measuring the light reflected by the leaves at different wavelengths, especially in the visible and near infrared. They can be used to calculate vegetative indices such as NDVI, which allow estimating plant vigor, the amount of chlorophyll, or the general state of health. These sensors do not require contact with the plant and allow detailed maps of variability within the vineyard to be generated. Thermal sensors measure the temperature of the leaf surface. A vine that is underwater, stress usually closes its stomata to prevent water loss, which reduces transpiration and causes an increase in leaf temperature. Thermal analysis is therefore a very effective tool to detect areas in need of irrigation, even before there are visible symptoms. Fluorescent sensors, on the other hand, capture the small amount of energy re-emitted by chlorophyll when excited by light. This fluorescence is a direct indicator of photosynthetic activity and thus of the physiological health of the plant. They are especially useful for detecting stresses before they become visually evident, such as those caused by disease, lack of nutrients, or adverse weather conditions. Transmittance meters, such as the well-known S-pad devices, work by placing the sensor in contact with the leaf and measuring how much light passes through the plant tissue. This allows estimation of chlorophyll concentration and, by extension, the level of nitrogen in the plant. Although they require physical contact and are slower to cover large areas, they are inexpensive and easy to use. In terms of sensors that analyze the structure of the vineyard, 2 technologies stand out: LiDAR and ultrasonics. Both measure distances to estimate the height, density, and volume of the plant canopy. LiDAR, using lasers, generates highly accurate 3-dimensional point clouds, ideal for assessing vine architecture and designing pruning strategies or targeted treatments. Ultrasonic sensors, although less accurate, are cheaper and sufficiently useful in many practical applications. Finally, soil sensors include technologies such as electromagnetic induction, EMI, and electrical resistivity, ER. EMI sensors do not require contact with the soil and allow large areas to be mapped quickly to assess soil texture, moisture, or salinity. ER sensors, on the other hand, require the insertion of electrodes into the soil but offer higher accuracy. Both types are essential for understanding soil variability and planning differentiated irrigation and fertilization management. Taken together, these technologies do not compete with each other but complement each other. A truly effective precision viticulture system is based on the integration of several of them, adapted to the specific needs of each farm and the resources available. Real cases of application. Proximal sensing technology is not just a theory, but a tool that is already being applied in real vineyards around the world with concrete results. In New Zealand, many wineries have adopted the use of drones equipped with multispectral sensors to calculate the NDVI of the vineyard. This index makes it possible to differentiate between areas of higher and lower vigor, and to plan the harvest in blocks with different qualities. In some cases, the grapes are even harvested separately and vinified in a differentiated manner, improving the quality of the wine. In arid areas such as California or La Mancha, where water is a critical resource, thermal sensors have been implemented in tractors or fixed stations. These sensors help to detect areas of water stress before the plant shows visible symptoms. Irrigation can then be applied in a localized manner, reducing water consumption and improving efficiency. France has pioneered the use of machine vision in the field. Using RGB cameras mounted on tractors or mobile platforms and using artificial intelligence algorithms, visual patterns indicative of diseases such as downy mildew, powdery mildew, or botrytis are identified. This allows quicker and more accurate action to be taken. SPAD or at-dot leaf type sensors are common in many Spanish and Argentinian vineyards. These portable devices allow measuring leaf chlorophyll in the field and estimating the level of nitrogen in the plant, facilitating fertilization decisions without waiting for laboratory analysis. On the other hand, more advanced technologies such as LiDAR are starting to be used to measure canopy volume with high precision. This makes it possible, for example, to adjust the height of pruning or to regulate the amount of crop protection spray applied according to the density of vegetation, which improves yields and reduces environmental impact. Finally, electromagnetic induction, electrical conductivity (EMI) sensors have been successfully used in Australia and Chile to map soil variability. This has facilitated the zoning of vineyards, allowing irrigation or fertilization practices to be adapted to the specific conditions of each area of the vineyard. These examples show that proximal sensing is no longer a distant future, but an evolving reality that improves profitability, quality, and sustainability in viticulture. Section 3. Installation, calibration, and maintenance. What factors should be taken into account when installing sensors in the vineyard? The installation of sensors in the field is a critical phase to ensure that the data they collect are reliable, representative, and useful. It is not enough to just put the sensor in place. Installation must be done with sound technical criteria. 1. Location. The location where it is installed should be representative of the behavior of that area of the vineyard. Sometimes multiple sensors are installed to cover areas with different vigor, soil types, or sun exposure. They can also be placed in problem areas for special monitoring. 2. Height and orientation. Each type of sensor has its own requirements. For example, a thermal sensor should not receive direct sunlight or be near reflective surfaces. A reflectance sensor should be placed at a constant height above the canopy. A soil moisture sensor should be installed at different depths depending on the root profile. 3. Fixing and protection. Sensors must be firmly fixed, resistant to wind, rain, hail, and even accidental contact with machinery or animals. In some cases, it is necessary to install watertight boxes, covers, or protective cages. 4. Power source. Some sensors are powered by rechargeable batteries, others by solar or mains power. It is essential to check their autonomy and provide for the necessary maintenance. 5. Data transmission. There are sensors that store data locally, requiring manual download, and others that send it automatically. Depending on the location, Wi-Fi, mobile networks, SIM, long-range radio frequency, LoRa, Sigfox, or even wired connections can be used. Network coverage and reliability are decisive factors. Correct installation not only ensures data accuracy, but also reduces the risk of failures, reading errors, or loss of information. It also facilitates future maintenance and integration with other technologies in the vineyard. What is sensor calibration, and why is it so important in precision viticulture? Calibration consists of adjusting the sensor so that its reading corresponds as closely as possible to an actual value measured by a standard method. It is an essential step to ensure that the data generated are reliable and comparable. In the case of soil moisture sensors, for example, even if the device indicates a percentage of moisture, that reading may not match the actual moisture if the sensor has not been calibrated for that soil type. To do this correctly, soil samples are usually taken. Their moisture values are determined by gravimetric methods in the laboratory and compared with the sensor readings. From there, a calibration curve specific to that texture or condition is generated. Optical sensors, such as reflectance or fluorescence sensors, also require calibration. In this case, reference plates or standards with known reflectance are used, or the sensor readings are compared with standard spectrophotometric measurements. Calibration corrects deviations of the sensor itself due to manufacture or use. Adapt the sensor to the specific environment, soil type, vine variety, environmental conditions. Increases the reliability of data in long-term analyses, predictive models, or comparisons between years or plots. It avoids serious errors in decision-making, such as unnecessary risks, over-fertilization, or a misdiagnosis. In addition, some sensors may lose accuracy over time or due to adverse conditions, heat, humidity, dust, so it is recommended to establish a regular recalibration schedule, especially before the start of key campaigns such as fertilization or harvesting. What maintenance tasks must be carried out to ensure the correct functioning of the sensors in the vineyard? The initial installation and calibration of a sensor is only the beginning. For optimal performance throughout its lifetime, regular maintenance is essential. This maintenance not only ensures accurate readings, but also prevents technical failures, data loss, and costly premature replacements. One-dot cleaning for optical sensors, RGB multispectral thermal, even a thin layer of dust or splashes can significantly alter the results. It is recommended to clean with soft cloths and suitable products without damaging the optics. In buried sensors, humidity EC, it may be necessary to remove and clean them periodically, especially in clay soils or soils with salt accumulations. Two-dot visual inspection. Regularly check the condition of cables, connectors, anchoring structures, and housings. Constant exposure to sun, wind, rain, or the passage of animals and machinery can cause damage that may affect operation. Three-dot power check. Sensors that rely on batteries should be checked to verify their charge. If they are powered by solar panels, they should be cleaned and checked for shading. It is also important to check wiring and electrical connections. Four-dot communication and data. Verify that sensors are sending data correctly. This involves checking the link to mobile networks, Wi-Fi, LoRa, or internal systems. It is also important to check synchronization with cloud platforms and that there is no loss of records or interference. Five-dot firmware and logging. Some sensors have internal software that can be upgraded. Keeping it up to date can fix bugs, improve functionality, or add compatibility with new platforms. Keeping a log of revisions, calibrations, detected errors, and applied adjustments is a good practice that helps anticipate problems and improves traceability. Section 4. Data Management and DSS. What does it mean to structure and standardize sensor data, and why is it crucial in precision viticulture? Proximal sensors generate a large amount of real-time data. This data can be of enormous value, or completely useless if not managed correctly. This is where the structuring and standardization of information comes into play. One-dot structuring data means organizing it in a coherent and useful way. This means assigning each piece of data a context, knowing in which plot it was taken, with which sensor, at what time, under what conditions. For example, a moisture data must be linked to the depth of the sensor, the soil type, and the vineyard block. Two-dot normalizing is the application of a common format. If data are collected from different sensors, each sensor might use a different scale. For example, degree C versus K percentage versus dimensionless rate. I say in order to be able to compare and interpret, it is necessary to convert them to standardized and unified units. Three-dot proper storage involves using relational databases or cloud platforms that allow data to be easily retrieved, viewed, and exported. In addition, it is key to implement security measures, backups, and access control to maintain the integrity of the information. 4. Integrating the data means combining it with other layers of information: soil maps, climate data, phenological calendars, treatment records, etc. This integration multiplies the value of each data, allowing cross-analyses and more complex patterns. 5. Once structured, normalized, and stored, the data is ready to be used in decision support systems, DSS, or mobile management apps. These tools could not operate without a well-organized database behind them. Structuring is not just an IT issue, it is the backbone of the entire precision viticulture strategy. It is what transforms data into knowledge, and knowledge into action. What is a decision support system, DSS, and what role does it play in precision agriculture? A DSS, decision support system, is a tool that transforms raw data into processed and useful information for decision-making. It does not replace the farmer or the technician, but it helps them to decide with more judgment, anticipation, and precision. These systems integrate information from field sensors, humidity, temperature, NDVI, etc., climate data, current weather and forecast, phenological and agronomic models, performance and treatment histories. Once all this information is integrated, the DSS analyses and compares the values with established thresholds, cultivation rules, or predictive models. The result can be an early warning, risk of disease, need for irrigation, a concrete recommendation, delay harvesting, adjust fertilization, a simulation or prediction, maturation curve, yield estimation. There are simpler DSS based on fixed rules. If the NDVI value is below 0.3, then apply fertilizer, and more complex ones, with artificial intelligence that learns from historical data and adapts to each plot or year. Today, many DSSs are integrated into web platforms or mobile apps, allowing them to be consulted from the vineyard in real time. Some even allow systems to be triggered automatically, irrigation, climate control treatments, although this requires high levels of automation and trust. How have mobile platforms transformed decision-making in the vineyard? Digitalization has reached the wine grower's pocket. Thanks to the development of mobile apps and cloud platforms, it is now possible to consult, interpret, and act on vineyard data from a mobile phone or tablet without having to be physically in front of the sensor or in the office. These tools allow 1. Visualize maps and indicators generated by the sensors and the DSS. For example, an NDVI map showing the vigor of the vineyard by zones, or a graph of soil moisture throughout the week. 2. Receive alerts and recommendations. The app can warn you if an area becomes water-stressed, if there is a risk of disease according to the climate model, or if a critical temperature threshold has been exceeded. 3. Remote and real-time access. Even if you are away from the vineyard, you can see what's happening thanks to IoT connectivity and data transmission from sensors to the cloud. 4. Record manual observations. Many apps allow the technician or farmer to add photos, notes, or on-site assessments, thus enriching the database with qualitative information. 5. Interaction with other technologies. Some applications are integrated with automated irrigation systems, weather stations, or even machinery, allowing actions to be triggered from the mobile phone itself. This immediate visualization and action capability improves operational efficiency, speed of response, and quality of technical monitoring, reducing unnecessary travel and centralizing all information in a single interface. In short, the mobile phone has become a strategic agronomic tool, capable of connecting the wine grower with the field at all times. Section 5. Challenges and mitigation strategies. Why can big data become a problem, and how can we manage it effectively? One of the side effects of agricultural digitalization is the so-called agronomic infoxication. Sensors generating thousands of data daily, each with different variables, formats, and locations. What in principle is an advantage can become a management and analysis problem if it is not structured correctly. Each sensor can generate tens to thousands of records per day. Multiply that by the number of sensors in the vineyard and by the number of days in the campaign, and you get an unmanageable volume without the right tools. To prevent this sea of data from becoming an obstacle, several strategies are recommended. 1. Intelligent classification. Organize data by vineyard area, type of variable, depth, phenological moment, or date. In this way, you can quickly filter them according to what you want to analyze. Two-dot hierarchical tagging. Each record should include metadata, sensor type, GPS location, date, environmental conditions, etc. This facilitates fast and segmented searches. Three-dot scalable storage. Use relational databases or cloud platforms such as AWS, Azure, Google Cloud, or agriculture-specific solutions that allow remote access, backup, and dynamic visualization. Four-dot automation of analysis. Set up dashboards that automatically update KPIs, key performance indicators, use algorithms to detect outliers, or automatic cleaning and processing scripts with Python or R. Five-dot quality filtering. Defining which data is relevant and which can be discarded due to redundancy, error, or low reliability. This reduces the overall volume and improves the quality of the analysis. So the challenge is not having too much data, but not knowing what to do with it. Turning excess into utility is a matter of digital design, agronomic judgment, and the right tools. What are the main reasons why many farmers are not yet adopting sensing technologies, and what strategies can facilitate their uptake? Although the benefits of sensorization are widely demonstrated, its adoption in the vineyard is not as widespread as might be expected. This is due to a combination of economic, technical, cultural, and structural factors. One-dot initial costs. The investment in sensors, stations, communication nodes, software licenses or apps, and their annual maintenance can be a barrier for small or family farms. In addition, the amortization of this technology may take several years. Two-dot technical difficulties. Many farmers have no knowledge of connectivity, databases, calibration, or maintenance. Added to this is the possible lack of network coverage, Wi-Fi, LoRa, mobile, in rural areas. Three-dot lack of training. Although many wine growers use smartphones, few are trained to interpret NDVI maps, set up a DSS, or check a thermal curve. This leads to dependence on the supplier or rejection for fear of mistakes. Four-dot insufficient technical support. Lack of specialized companies in rural areas or difficulty in accessing specialized technical service leads to frustration and abandonment of systems. Five-dot little adaptation to small scale. Many systems are designed for large estates or technological companies. Small vineyard plots require more modular, affordable, and simplified solutions. How to facilitate adoption? Through continuous training and technical support promoted by cooperatives, associations, or public services. With accessible business models, subscription per use rental scalable solutions. Promoting specific public aid for agricultural digitization. Developing simple visual interfaces in agricultural language so that the user does not need advanced knowledge. The digital transformation in viticulture is not only technological, it requires a social and educational strategy that empowers the wine grower as the protagonist of change. Conclusions and references. Conclusions and vision for the future of proximal sensing in viticulture. Throughout the module, we have seen how sensors can transform vineyard management, making decisions such as when to irrigate, how to prune, or where to harvest not based on intuition, but on real, accurate, and localized data. Sensorization improves. Efficiency, less resources, more output. The quality of the final product, selective harvesting, optimal ripening. Sustainability, rational use of water and fertilizers. And above all, the ability to anticipate problems before they occur. But we have also seen that data alone is not enough. They require structure and standardization, analysis and visualization, decision tools, DSS, training to interpret and act. The future of sensorization will be more accessible, cheaper devices connected by more efficient networks, more autonomous, sensors that calibrate themselves, communicate with each other, and alert automatically. Smarter, integration with predictive modeling, artificial intelligence, and comprehensive management platforms. And above all, it will be more humane because it does not replace the farmer, but empowers him with real and useful information to make better decisions. Here are the main references we used throughout this lesson. And this concludes our lesson. Hope you enjoyed it. Thanks for tuning in.